Hi, I'm Nicholas Dwork, and today we're going to be discussing partial Fourier and compressed sensing, two other methods for accelerating MRI. Recall that MRI is a Fourier sensing modality, so the data that we get out are Fourier values in the frequency domain. If we collect enough data, we could just perform an inverse discrete Fourier transform, and that reconstructs our image. Recall this is the discrete Fourier transform. It's a sum of exponentials, and it can be represented as a matrix multiplication. It's an invertible operation. Now we're going to ask the question, what if G is real? What if we know that G is real? What relationship can we identify in the Fourier values? Recall that an exponential can be expressed as a sum of a cosine and a sine. Simply distributing the sum across the subtraction gets us this expression. And now we're going to ask the question, what is G of minus k? Suppose we know G of k, how does it relate to G of minus k? We start by just replacing k with minus k everywhere we see it inside the cosine and the sine. Because cosine's even and sine's odd, this simplifies to this expression. This can be expressed as a sum of complex exponentials. Hopefully you can see that this is just G of k conjugated. So how do we use this? What this tells us is that if we know some value in the Fourier domain, we automatically know another value, this other value, along its diagonal. It's just the conjugate of the original Fourier value above. So if our image was real, then we could only sample half the Fourier space and still reconstruct a high-quality image. Unfortunately, our image is not real because of inhomogeneities in the main magnetic field or in the excitation pulse or errors in the gradients. So what do? We collect more than half, slightly more than half, about 5/8 of the data. Then we use the center region to estimate the phase. Assuming that's the phase, the rest of the image is real, and we reconstruct accordingly. So here are some results. This is an axial slice of a brain. This is a fully sampled reconstruction. This is what happens when we reconstruct with only 5/8 of the data, but we leave all the other values equal to 0. And this is the partial Fourier reconstruction where we take advantage of the low frequency estimate of the phase and the conjugate symmetry in the Fourier domain. As you can see, it's a much higher quality than the zero field reconstruction. This is available on clinical systems and is commonly done. Okay, so we've discussed partial Fourier. Now let's discuss compressed sensing. Here are 5 images of various things, including the sagittal slice of the knee, a dog eating ice cream, the pentagon, a woman, and a man. And here are their wavelet transforms. It's very easy to notice that their wavelet transforms are almost all black. The predominant intensity you see is black. And this is notable. What this tells us is that if we just knew a few of the wavelet coefficients, the highest wavelet coefficients, then we could reconstruct the image very accurately. Compressed sensing takes advantage of this property. Like parallel imaging before, compressed sensing will reconstruct an image as a result of an optimization algorithm. Here, X is the hypothetical image, F is the discrete Fourier transform, and M isolates the values for those frequencies that were collected. If the image X is correct, then we would expect the vector MFX to be very close to B, within an epsilon bound, where epsilon is an estimate of the amount of noise. Here, W represents the wavelet transform. And so this says, make the wavelet transform of X sparse. That is, make most of the values of the wavelet transform of X 0. Here we're going to use only 33% of the samples, and they were collected according to a variable density sampling pattern. Each white point here represents a sample in the Fourier domain that was collected, and each black point represents one that was not. If we reconstruct the image by solving this optimization problem, then we get this result, which is very close to the original fully sampled reconstruction of the knee. And now this data could be collected 3 times faster. Here are some notable references. Thank you for your attention.